All right, up to this point, in chapter 8, we looked at bonding in terms of ionic bonding, and then we started introducing covalent bonding with the valence bond theory. And we were able to construct three-dimensional models of our molecules by drawing the Lewis dot structure and then proceeding through VSEPR to a three-dimensional structure. And that works pretty good as far as it goes. The problem is it doesn't go far enough. It doesn't tell us anything about the energy levels of the bonds. Now we can do the calculations for transitions and how much light can be absorbed of a certain wavelength and emitted. That works reasonably well for hydrogen-like molecules. But if you want a complete model of the molecule of any size, then we need a better theory. First thing we're going to do, though, is look at the problem. With the Lewis structure for methane, the shape of that methane molecule, remember, should be, if we draw the Lewis structure, CH4, then we're going to have this, and that. I've used up all the electrons. 6 plus 4 is 10, 4 plus 4 is 8, 2, 4, 6, 8. So that's good. And the structure should be tetrahedral. And all the physical evidence confirms that. The shape of this molecule is tetrahedral. And the bond angles are 109.5 degrees. Bond angles. Okay, here's the problem. With the valence bond theory, look at the electronic structure of each one. Right, the hydrogens are all 1s1s. Okay, so that's no big deal. The carbon, though, is 1s2, 2s2, 2p2. 6 here, 1 there. If we try to bond 2 of these, you get 2 bonds with these, right? We get a hydrogen here, get 2 hydrogens bound. Remember, the valence bond theory says you overlap atomic orbitals. Each atom retains possession of its electrons and orbitals, but they share them. So if we're going to share these 2, we get, remember, it can be subdivided into X, Y, and Z, right? So we can get a sharing here and a sharing here. And based upon the geometry of the p orbitals, right, you get some going like this, and you get like that, and then like this. So we could get a sharing here of that hydrogen, maybe a sharing here of this hydrogen. That would put them at 90 degrees to each other, right? And that's not what we see, 109.5. But then if you try to overlap the s orbital is like this, and you orbit like that, and that's 180 degrees. So you see the problem. The model doesn't fit the evidence. So, right, remember we have options for fixing problems. Right, we can either modify the theory, right? We can restrict its use, and to some extent we do that. We can throw it out and start over, right? We're not at that point yet. Or you can turn it into a religion, but we're not there yet either. All right, so what are we going to do? Well, the proposal, right, there's the problem. The proposal was a modification. If we're going to have 4 equivalent orbitals so that they can all be spaced out at maximum distance for the electron repulsions, then we need to create a concept called hybridization. Hybridization. So what we're going to do is take this s orbital from carbon and the p orbital, and remember the p orbital has 3 of these, and the s has 1 of those. So we can take these 4 and morph them into 4 hybrid orbitals of this designation, sp3 orbitals. Okay, if we do that, then we can theoretically and mathematically, of course, morph these into equivalent sp3 orbitals. So now that they're spaced properly for the evidence that we get from this molecule. So that's what we do. And of course, based on the valence bond theory, we have to hybridize the orbitals that are on this atom, because those orbitals still belong to that atom. I mean, that's a central tenet of the valence bond theory. These orbitals, these electrons, still belong to that atom. They just share them. Now that we've got hybrid orbitals that belong to that atom only, we can share each one of those equally with these hydrogens and get the structure we want. All right, this concept was proposed by Linus Pauling. Remember, he was the one that I mentioned, published a book called The Nature of the Chemical Bond, and he got a Nobel Prize for it. But he proposed this modification to the theory in 1931, and it worked pretty well, right, for a number of years. It still had the same problem. Even after this hybridization, we could account for the geometry, but we still can't account for the energy. We can't calculate energy using this model. All right, so we're getting there. Now, of course, the quantum mechanical equations that were used to give us the electronic structure of carbon, they had to be modified so that they could accommodate and predict these orbitals. So it wasn't an easy task. I mean, it was a brilliant idea, but it still required a lot of work in the math to get it to come out correctly with the formulas, because we're still in quantum mechanics. Okay, so this is what a hybrid orbital looks like. These orbitals don't exist unless the bonds form. In other words, the hybridization occurs during the bonding process. Okay. Otherwise, it's just like that. It just stays that way. They only hybridize when they're needed. Okay. Now this is not to imply that we know exactly what the energies are, but we can sort of qualitatively or semi-quantitatively identify where we think the energy levels will be for these hybrid orbitals. There's something of a, since they're hybrids, then they have S character and P character in terms of energy. The S's are lower in energy than the P's, just slightly lower. So when we hybridize them, the hybrid orbitals should have an energy that's more closely related to the P's, because there are 3 P's and only 1 S. Okay, so they have 75% P character and 25% S character. It's an easy way to look at that. And that's sort of a weighted average of what you can expect the energy level to be for those orbitals. And we've used the quantum mechanical models to calculate and present a visual model of what we think they would look like. And notice all these orbitals are pointed at 109.5 degree angles from each other. And this is what we suspect that the models would look like. right? We don't know. We can't actually see it. But that puts everything into a regular tetrahedron. Okay. So let's try this model for ammonia and see if it can work for ammonia too. So the ammonia model, if we have the Lewis dot structure of VSEPR for ammonia, we get an electronic structure for ammonia of a tetrahedron with with a lone pair at the apex. If you remember the structure there, I think I've got a picture of it here. There it is. So this would be a valid Lewis dot structure, and well, that doesn't show. And with nitrogen in the middle, and if we have a let's see, in the back here, we have hydrogen back here. We have hydrogen here, hydrogen here. This nitrogen needs to be a little bit higher, like that. And then we have our lone pair up here. Okay, so we have a bond there, a bond there, a bond there, and lone pairs. So this gives us a trigonal pyramid for the molecular structure. The electronic structure is still tetrahedral because you have these 4 positions in that one. Now the bonds are going to be modified somewhat. The bond with this pressure from these electrons, the bond angle is going to be shrunk a little bit. It would be closer to maybe 107 or something like that. Okay, so we act with 4 electron pairs. We have a tetrahedral electronic structure. And with a tetrahedral electronic structure, focusing on that central atom, it still must be sp3 hybridized. Produce these 3 orbitals here, 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 and here, right? But that one is occupied by a lone pair. Okay, and that's the artist's idea of what it should look like. Okay, let's try another one. We get a bigger molecule this time. So with ethylene, sometimes we say ethene, but ethylene is correct. Now we have 2 times 4 is 8, and 4 is 12. So we have 12 electrons, and we're going to connect the carbons to each other and then put the hydrogens out here, like that. So 2, 4, 6, 8, 10. We got 2 electrons left over. We put them there, and then when we make the octet, of course, we make a double bond. So that gives everybody an octet, and the structure around any of the central atoms, carbons will be the central atoms. This will be trigonal planar. Around either one of the carbons. So how do you make trigonal planar? How do you make an equivalent, 3 equivalent orbitals around carbon that give you a 120-degree bond angle? Well, you got to use the lowest energy, of course, and then you only need 2 more P's, right? Because you get the same number of hybrid orbitals as you do atomic orbitals that go into the mix. So if we put 1 in S's and 2 P's in there, then we get 3 equivalent sp3 or sp2 orbitals. So each one of these is formed from sp2. Okay, around the carbon. So what does that do for carbon? Well, carbon's got these equivalent like at 120-degree angles. These are the sp2s. Well, it's got a p orbital left over. That p orbital just sits out here like this. Right? That's the unused p. Okay. So what do we do with the unused p? you do a sideways overlap. Like that. And that's your double bond. That's the second bond. So the single bond that we form between the carbon, this carbon and those hydrogens is sp2 hybridized. But the second bond of the double is formed from overlap of unused p orbitals. Okay. So we got trigonal planar and 120-degree angles, and there you go. So let me start building a table over here on the side. Let's see, how do I set this up? Electron groups around the central atom. Right? So if we have two, of course, we know that the electronic structure is going to be linear. If we have three around the central atom, then we know it's going to be trigonal planar. That's this example. If we have four around the central atom, it's going to be tetrahedral. Okay. If we have five, remember, it's going to be a trigonal bipyramid. If we have six, it's going to be octahedral. Okay, that's the electronic structure. Now we can draw molecular structures from each one of these if we have lone pairs. You just cover up the lone pair and see what's left. But for hybridization purposes, this is as far as we need to go. We don't have to go any farther than this because this is where we get our information for hybridizing. Okay, so let's see. I put this one here. Hybridization. Well, for linear orbitals, I don't think you need hybridization. We've covered this one already, right? This one is sp3 hybridized. Right, so we have four equivalent sp3s. This one we have three equivalent sp2s. And I might put this one plus 1p left over. How about that? Okay. Let's see. Now, trigonal planar. Okay. Yeah, we covered that. We're going to talk about sigma versus pi bonding in just a minute. So hold on that topic. Well, we're ready already. Single bonds. If you have an atom here and an atom here, and the electron density is distributed on axis between those two atoms, this is a sigma bond. You can only have one sigma bond on axis because there's only one axis. Okay. If you have a double bond, either this one, or if you have a triple bond, that's okay. You can have what's called a pi bond. You can have as many as two pi bonds also. And the pi bonds are sideways overlap. So what that means is the sigma bond is stronger than the pi bond because the pi bond doesn't get a good overlap of orbitals. Whereas on the axis, you can get as close as the atoms will allow you to get and get good overlap. But the sideways overlap is strained. So the pi bond itself, if we knew the energy of the pi bond, it would be less than the sigma bond. Okay. And these are I should say sideways overlap of p orbitals. Right, we've seen an example where we only have one available p here, just sideways overlap. That's okay. If we have two electron groups, and to get a linear arrangement, then we only need two sp orbitals. That means we have two unused p's left over. Let's see, I've got an example coming up. A word about the energies. Right, now we've got less p character to this one because there are only two of these. That means it has 67% p character and 33% s character. Right, so the energy is lower for the sp2 hybrid orbitals. Okay, and this is what we're trying to show you. The sp2 hybrid orbitals are in a plane with 120-degree angles, and then you got that extra p orbital sitting out there that can overlap sideways with its neighbors. And this is artist rendition, what we think it looks like. Okay. Yeah, there we go. We get the sideways orbital of the unused p's. Those, that bond, that second bond is a pi bond. And one of those lines is a sigma bond on axis, and the other one is a pi bond. Right? The two lines don't show you that. Right? You just have to know it. How about carbon dioxide? Well, let's see. CO2 says that we have 6 valence for this one, that's 12, and then 4 here. So that's 16 electrons. So we have a carbon, excuse me, 1 carbon and 2 oxygens. There we go. So that's 2, 4. We have 12 left over. 2, 4, 6, 8, 10, 12. Okay. Now we need to make an octet for carbon, and the formal charge method tells us that the lowest formal charge mix that you can get for this group is put a double bond on this side and a double bond on that side. So these oxygens have 2 lone pairs, and we have a sigma here, right? This is a sigma, and a pi, on either side of that carbon. Okay. So what are the bond angles? Well, we know the bond angle is going to be 180 degrees, right? Because we have 2 pairs, groups. We have 2 groups, electronic groups. So that means we're going to have a linear with a 180-degree angle. And this is 120 degrees. This is 109.5 degrees. Okay, so now the shape of the molecule is linear. Bond angles are 180 degrees. Now, let's see what hybridization is required. Well, we need two equivalent orbitals to give us 180 degrees. So we only need to hybridize S with one of the P's. So we get an sp hybrid. We get 2 sp hybrids. Right? One goes to this side and one goes to this side. And we have 2 unused p orbitals. Okay, that's just for the carbon. Now the energy for this is going to be much, much lower. The sp has only 50% p character and 50% s character, so the energy level is going to be lower still. And then we have those 2 unused p orbitals. Okay, what does that mean for the actual bonding? Well, they're the hybrid orbitals that give you the 180-degree angle, but we've got the unused p orbitals. right? We got going this direction and this direction. Right? One into the plane, one with the plane, or into the plane, one. Let's see, we can go this way, and go this way. So those unused p orbitals can be used for our double bonds. One of them will be a double bond on this side, and the other will be a double bond on that side. But since those unused p orbitals are at right angles to each other, we get a double bond in this plane, maybe over here, and in this plane over here. Right, so they have to be right angles to each other. That's what we're trying to show here. Also, the oxygens have to be hybridized also in order to provide the correct electronic orbitals to overlap. So if this oxygen has 1, 2, 3 groups around it, it's trigonal planar, which means it has one unused p, like that. This one, see, one unused p. This is trigonal planar. So these lone pairs are going to be at 180, 120 degrees from this sigma bond. And then this unused p orbital can overlap. So that's what we're trying to show here. All right. So who's next? Nitrogen. The nitrogen molecule. If we drew that as a Lewis structure, nitrogen has 5 each, so that's 10 electrons. We have nitrogen here. That's there, so that's -2 is 8. 2, 4, 6, 8. Let's do it like this. There we go. Yeah, we can take this to make a pi bond, take this one to make a pi bond. Let's move these over here. So we have lone pair here and a lone pair here with a sigma bond in between them. Okay. Each atom is surrounded by 2 effective pairs. Right? So what we need here is 180-degree angle between this one and that one, which means sp hybridized. So this is sp hybridized here, and of course on this side. And then that means we have 2 unused p orbitals left over that can overlap. And a p orbital on this one and this one, they overlap, and then a p orbital, the other p orbital overlaps in this plane. Okay. So nitrogen has 1 sigma and 2 pi's. You can't have a pi unless you have a sigma first. Okay. So this is the artist's idea of what it looks like. Okay, let's go step it up a little bit. All right, we've come up to tetrahedral. Now let's go to PCl5. Right? Phosphorus will have 5, and 5 times 7 is 35 for the chlorines. So that's 40 electrons. All right, so we have phosphorus, and we have 5 chlorines around it. That should use up all of our electrons. So we got 6 around each one. 6 times 5 is, let's see, 2, 4, 6 times 5 is 30. Then 2, 4, 6, 8, 10 is 40. Okay, so we used them all up. All right, if we have 5 effective groups, like this one, that's a trigonal bipyramid. So we need the trigonal arrangement here, and then we need a chlorine up here and a chlorine down there with a phosphorus in the middle, a chlorine in the back, chlorine, chlorine. So we got this bonded to here, 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 here. Okay, so what possibilities do we have? Well, on the triangle, we have 120 degrees. And this one here would be 180 degrees. And going from here to here or here to one of these is 90 degrees. That's the most effective way to construct this molecule and minimize repulsions. So we know the shape from our VSEPR is trigonal bipyramid. And they're the bond angles. Okay, how do we get that? Because from this point, we've used up all our p orbitals, right? We need 5 hybrid orbitals. Well, how do you get 5? Well, look at the phosphorus. Where's phosphorus? Phosphorus is in the third period. 3s, 3p, 3d. It has access to d orbitals. Right? So we use one d orbital. Let's see. I don't know why they do this, but they do. They put the d in front, dsp3. So we use one d orbital, one s orbital, and 3 p orbitals, and we get 5 equivalent hybrid orbitals that are pointing in these directions. And I can only assume that the d orbital character is what causes these, what looks like discrepancies in the angles. But the physical evidence tells us that this is true. This is the correct structure. So we got to make the theory fit the evidence. And that's the best we can do under these circumstances. DSP3 hybridized. And they're all sigma bonds. We don't have any free p orbitals or d. Well, we got free d orbitals, but we don't need them. We only needed one. And besides, those other d orbitals don't have any electrons in them, so they're not going to bond anyway. Okay, how about the Lewis structure for xenon tetrafluoride? Okay. This has 8 valence electrons, and 4 times 7 is 28. So that equals 36 electrons. So we have xenon in the middle, and we have 4 fluorines, 2, 4, 6, 8. So that's 28 electrons. 6, 2, 4, 6, 2, 4, 6, 2, 4, 6. So 6 times 4 is 24. And that's 4 electrons left over. So we have 2 here and 2 here. Okay. All right. We have 6 groups around that xenon, so we're octahedral electronic structure. Right. How do you do that? Well, we just raise our bet. We raise our bet. With 6, we need 6 hybrid orbitals. We just use 2 Ds. And that gives us 6 orbitals. Okay, so the structure is going to be octahedral. The bond angles are only going to be 90. Why? Because these lone pairs in an octahedral structure are positioned at the apex. So we'll have up here and down here, xenon in the middle, bound to each of these fluorines. And that angle is 90 degrees. But for determining what the hybridization needs to be, we have to consider the octahedral layout. And this is going to be 90 degrees here if there were something there besides the electrons. But the bond angle is 90 degrees. And we're D2 sp3 hybridized. So there should be a pattern emerging here. If you need 2 electron groups of equal construct, Then you hybridize an S and a P. Get two of those. All right, 1, 2. 3 means 1, 2, 3. 4 means 1, 2, 3, 4. 5 means 1, 2, 3, 4, 5. And 6, 1, 2, 3, 4, 5, 6. That's why I put this table up here to try to show a logical progression. Okay, and that's the hybridization. 6 equivalent hybrid orbitals. Now we know that this fits the data because the physical evidence tells us that this molecule is square planar. Right? If it weren't square planar, then we would have a dipole. There's no dipole for this molecule. It's completely nonpolar. Okay. Oh, there it is. In black and white. That's good practice for me too. Okay. How about the Lewis structure for HCN, showing all the bonds between the atoms, labeling each bond as a sigma or a pi? We've done this one before. I'm going to do it from scratch, just in case we need to do one that we haven't done before. Okay, so that's 1 electron, 4 electrons, and 5 electrons. All right, so that's 10 electrons. So we have C, and N. We've used up 4, means 6 left over. Start from the outside and work our way in. 2, 4, 6. Then we need to make an octet. Can't do it from this side because hydrogen can only have a duet. So we move 2 over here, 2 over here. That's our Lewis structure. So we have a sigma bond on this side, we have a sigma here, and we have 2 pi's. Okay. Now the hybridization requires that we need equivalent orbitals to hold both the bonding pair and the non-bonding pair. So this is going to be sp hybridized to give us 2 equivalent orbitals in those directions. This one also has 2 bonding pairs, so it's sp hybridized as well. That means that we have 2 unused p's here, 2 unused p's here, so we get the overlap of 2 of them to give us 1 pi bond, and the other 2 give us the other pi bond. There's our sigma, and 2 pi's. Okay. Now let's see if we're as good as we think we are. Well, we did ammonia already, so and we did carbon dioxide, so I'm going to skip those. Let's go to sulfur dioxide. Okay, so sulfur and oxygen are the same number of valence electrons. So 3 times 6 is 18 electrons. We have sulfur, we have an oxygen and an oxygen. 2, 4. So that's 14. 2, 4, 6, 8, 10, 12, 14. Right? Well, sulfur only has 6, so we have to make a double bond on this side. And we could draw an equivalent Lewis structure with a double bond on the other side, which means we're talking about resonance. But we're going to stick with this one because it's easier to work with just one and try to work with 2. Okay, so what's our structure here? Electronic structure is trigonal planar. Okay, with 3 groups, trigonal planar means we have sp2 hybridization. All right, so that means we have 3 sp2 hybrids, a sigma bond on this side, a sigma on that side, and a lone pair on that side occupying the other one. And then we have 1 p. Now, the same thing happens with this one. Well, actually, for this one, that oxygen is not hybridized. This oxygen is hybridized so that it can give us the same hybridization, three sp2s and one P. But this side, well, actually, this side is sp3 hybridized because it has 4 groups around it. So this one's sp3, this one's sp2, and this one's sp2. Okay. Well, we did that one already. And this one, sp2 hybridized on the sulfur atom. We're looking for central atom hybridization. So we essentially ignore these two. Now, the problem with this scenario, sp2 on this side and sp3 on that side, says that these are different bonding patterns, but they're not. They're the same. These are equivalent on both sides. So there we see another fault of the valence bond theory. We know that the physical evidence says these are equivalent on both sides. So our resonance was the workaround for that. But in reality, those bonds on either side are equivalent. All right, who's next? Oh, krypton difluoride. Okay, so that's 8, and 2 times 7 is 14, which is 22 electrons. Okay, so we have krypton, and we have fluorine on both sides. So that's 4 is, that's 8, right? 18. So 2, 4, 6, 8, 10, 12. We got 6 left over. 2, 4, 6. Right? So if we've got 5 groups around the krypton, well, actually, this one's already got an octet. And krypton exceeds the octet. So we don't have to make any pi bonds here. But the geometry with 5 groups is trigonal bipyramid. Trigonal by, oops, let me spell. Trigonal bipyramid. Okay, so what kind of hybridization do we need for this one? Well, if we have 5, this is dsp3. Okay. And if it's trigonal bipyramid, and we have 3 lone pairs, where do the lone pairs go? Let's see, let's do. So we have krypton in the middle. We have fluorine up here, fluorine down here, and the lone pairs go on the triangle. Okay. So the bond angle is 180 degrees. The linear molecule and nonpolar. We threw that one in for free. There's carbon dioxide. We did that one already. It's sp hybridized. Excuse me. And ICL5. ICL5. So that's 6 times 7 is 35 electrons. So we have I in the middle. We have 1, 2, 3, 4, 5 chlorines. 2, 4, 6, 8, 10. Minus 10 equals 25 electrons. Right? 5, 6 times. Oh, no. I'm sorry. 6 times 7 is 42. 42 electrons minus 10 equals 32 electrons. Okay. So there we go. 2, 4, 6. 6 times 5 would be 30. So we use up 30, making octets around chlorine. And we have 2 electrons left over. They go right here. So this molecule has 6 groups around the iodine, which is octahedral. And that means we need D2sp3 hybridization. So we have this square in the middle with an iodine in here. And where do the lone pairs go? Lone pairs in the octahedral go on the apex. So we're going to have a lone pair up here. We're going to have a chlorine here, 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 and here. So the bond angles are 90 degrees. Okay, with D2sp3 hybridization. Okay. All right. This is just summarizing everything, bringing it all together using the localized electron model. And then we describe the limitations. Electrons actually are not localized. We've learned that from experience. Because the resonance had to be added to this one to make it work. And you can't localize the electrons around one atom or the other and make this work in this fashion right here. So that's evidence that the electrons are not localized. They're actually spread out. They're delocalized. And in fact, the concept of delocalization of electron density stabilizes molecules. When you can spread them out further, you stabilize the molecule. And hopefully we'll get to a discussion of that later. Free radicals, yeah, I think we've had one molecule with a free radical. It was maybe a nitrogen oxide ion of some kind. I can't remember which one it is, but we had to put an electron in there all by itself, and that's very unstable. It doesn't provide direct information about bond energies. We had rough ideas of where the energies lie, but we don't have direct evidence and a way to calculate exact bond energies from the model itself. Okay. If we needed to, this is where I'd pause. But since we got the time, we carry on. Okay. So here's the solution to the problem. It's called the molecular orbital model. I'm going to leave that up there until I need the space. So this is molecular orbital model. The molecular orbital model, the main difference between valence bond theory and the molecular orbital model is that the valence bond theory is more like capitalism. Everybody owns their own electrons. And the molecular orbital model is more like communism. The electrons belong to the collective. So, in order to do that, we have to take the atomic orbital structure and throw it out as the molecule forms, take what we know about it, and morph it into an orbital structure for the entire molecule. Okay. Now, this is just a caveat. The concept of the orbital, as in, right, we go back to the Bohr model of the atom, and this is grandfathered in. Orbital is not really what we're looking at here. We're not looking at electrons doing this thing. But we use that term. We bring the term over because it's ingrained. We don't have much choice. All right, here are the differences between the localized electron model of the valence bond theory and the molecular orbital model. Right? The localized model requires atomic orbitals. molecular orbital model throws those out and converts them into molecular orbitals. They're both quantum mechanical. They treat the atoms as in quantum mechanical terms. And this is brought forward from the quantum mechanical electronic model of each atom is morphed into the molecular structure. So the hybridization had required some fancy mathematical footwork to get the equations to work. Now we go even further, and we have to modify those equations even further to encompass the entire molecule with a single set of equations. Okay, in the localized electron model, the electrons are assumed to be local. They belong to each atom. Whereas in the molecular orbital model, the electrons are delocalized. They belong to the entire molecule. We still have 2 electrons per orbital. So when we call something an orbital or a bond, then we have 2 electrons. The psi squared part of the wave function of the Schrodinger equations and the modifications as we bring them forward to the molecular orbital model, they're wave functions. And in the localized electron model, they're solved for the atomic structure. And we're still quantizing the energy. But in the molecular orbital model, that part of the model, which predicts the probability of finding an electron in a given space, that's what the psi squared is in there for, is applied to the whole molecule. All right, one thing that we do is if we go into a molecule with individual orbitals from the atoms, whether they're atomic orbitals or they're been hybridized, the same number of atomic orbitals that you go in with is the same number of molecular orbitals you come out with. So we conserve the number of orbitals. So if we overlap 2 atomic orbitals to produce 1 bonding and 1 anti-bonding, that's how we conserve them. So if we bring 2 atomic orbitals in, we have to have 2 molecular orbitals out. And the way we do it is one of those orbitals is at a low energy we call bonding orbital, and the other one is at a higher energy than the makeup of the atomic orbitals. So they kind of sandwich it. The anti-bonding orbital is a much higher energy. The bonding orbital is much lower energy than the atomic orbitals that make up, that are brought into the mix. I got a little video that talks about interference. Interference is a concept. The temptation is to think of interference as always negative. But in physical terms, interference can either be positive or negative. And when the video comes up, I think the video is coming up. Let me see. Steal my own thunder. Yeah. It's coming up next. So if the probability of finding an electron is between the atoms in the molecular orbital, then we say it's a sigma molecular orbital. And if it's off-center, then it's a pi orbital. And we can still only have 1 sigma orbital of a particular mix. Then the rest have to be pi's. Let's see. Right, once we've made our molecular orbitals, the atomic orbitals are in the garbage. Well, actually, they're not in the garbage. They've just put on different masks. They're molecular orbitals now.
Waves can overlap. When that happens, the highs and the lows can build upon each other. or they can align in such a way that they balance each other out. When they build upon each other, this is called constructive interference. When they balance each other out, this is called destructive interference. Let's look at what happens step by step when two waves travel through each other. Here's a moment when two highs overlap. This results in a combined high that's much higher. This is constructive interference. Now, here's a moment where all the highs are perfectly overlapping all the lows. We see a cancellation of the wave amplitudes. This is a moment of destructive interference. If you took a snapshot photo, you might think that nothing is happening. Change that to a video, and you'd see otherwise. In the next moment, you've got a case where the two lows are now overlapping. This results in a combined low that's much lower. Once again, we have constructive interference. So, constructive and destructive interference never occur at the same time. Instead, they alternate, one after the other. And then the two waves continue on their merry way, having traveled right through each other, amazingly unaltered. Check this out. A wave can bounce off of a rigid structure. Let's add a second wave. Cool. Let's add a second wall and try to confine a single wave. Aha. What we've got here is called a standing wave. Notice that to have a standing wave, the dimensions have to be just right, typically some multiple of the wave's wavelength. A musical instrument, such as a guitar or a flute, is engineered just right to accommodate standing waves, vibrating within the instrument, producing beautiful sounds. That's good energy.
Okay. So the idea here is that, and this was a representation in 2 dimensions, right? These molecules are in 3 dimensions. So we have to expand our thinking to think of waves that propagate in 3 dimensions. And that's a little hard for the human mind to manage. That's why we have computers do the calculations for us. But for a given atom, if we just have the atom, let's focus on an atom with an orbital here and an electron in that orbital. If you think of the electron as a wave, then you want that electron to have a wave that is perfectly constructed so that it is a standing wave at that distance from the nucleus. And then if you add energy to it, it moves to another location out here, another orbital, where its new standing wave incorporates all that extra energy and is another standing wave. So that's one way to rationalize the quantization of energy, is it can't occupy anything in between because we can't produce a standing wave in here. It has to be out to the next orbital, and so forth and so on. Okay. And we can expand that thinking into molecular orbitals to accommodate both the constructive interference, which would give you the lower energy, and the destructive interference that would give you the anti-bonding orbitals. Okay, so here's some terms. Superposition. That's just a term that describes the overlapping of waves. Interference, of course, is the interaction of 2 waves that meet. Constructive and destructive, we got a nice snootful from that video. They can form very complex patterns, especially if we're talking about 3 dimensions. And especially if they have different frequencies, we can get complex interferences. If you think of AM or FM radio, right? How do you get that signal, right? The signal that gives you the sound from one place to the other. Well, you have a static carrier wave, right? And that would be whatever, I don't know. FM, it might be 101.6 is talk radio, megahertz. So we would have that frequency for this wave, and then they would superimpose on that by interference, and it would make a more complex wave, something like that. And then at the other end, you have the device, the receiver, cancels out this carrier wave, right? It introduces a wave with destructive interference that removes this carrier wave, and you're left with the signal. That's how you get from one place to the other with the signal and not a bunch of noise. If you try to tune in a station, right, on your dial, you try to tune in a different frequency, then you won't get the station you're looking for because it won't cancel out the carrier. Now, there are a host of different ways. That's the analog way of transmitting information. Digital way is a little different, but it still incorporates the idea of superimposing or multiplexing signals on a carrier. Okay, so if we keep it really simple and we're looking at the hydrogen atom, we have one s orbital from each hydrogen atom, and we've got that plus sign in the middle is the one proton in the nucleus, and then the blue ball is the electron probability. So if we get, let's look at the bottom one first. If we get constructive interference, we're going to get a bonding orbital, a bonding molecular orbital from the 1s. Okay, but if the wave function is destructive interference, we're going to get the anti-bonding orbital. And notice that the electron density that's predicted through the wave functions is that there's a node between those two nuclei. Node means there's no electron density. So that's why we call it anti-bonding. It doesn't bond, right? Okay. That's the very simplest explanation. And this says just what I told you. Anti-bonding orbitals tend to be higher energy. They're always higher energy, and bonding orbitals are lower energy. Lower energy means more stable. Now, when we diagram these, we say, all right, here's the hydrogen atom here, and here's the other hydrogen atom over here. And then on this energy scale, right, we have 1s orbital for this hydrogen and a 1s orbital for this hydrogen. That's before they come together. Now, when they meet, this is the molecule in the middle. Okay? And when they meet, then these two orbitals disappear and we convert them into molecular orbitals. The bonding molecular orbital will be down here at lower energy. So this is a, let's see, I want to use the right symbols. This would be a sigma from the 1s orbitals. And this would be the anti-bonding, actually it should be a little higher. Anti-bonding, sigma from the 1s, and we use a star. Star means anti-bonding, just so we can tell them apart. Right? We usually draw tie lines like dotted lines. So these two atomic orbitals made this bonding and anti-bonding. Right? We started out with an electron here and an electron there. Okay. Okay, when we form the molecular orbitals, then those electrons go into this system. They disappear from that system and they end up in this system. And we use, excuse me, we use the Aufbau principle. In other words, electrons go in at the lowest energy first until it's full, and then we move up. So both of these electrons go in the bonding orbital. Okay. And the fact that we started out at these high energies and we ended up at this low energy with none in the anti-bonding means that we predict that this will happen. We will form that molecule. All right. Let's see. I think. All right. So when we use our symbolic language, we're trying to explain not just the energy, but the symmetry of the orbitals also, based upon their origins. So if these 1s orbitals morph into sigma bonds, then they're going to be on axis. Now, if they're bonding, they're going to be on axis between the atoms. And if they're anti-bonding, they'll be on axis, but they'll have a node in the middle. Right. And this is fairly consistent with the way we construct and we label the molecular orbitals. And we're consistent with the number of electrons that can go into each orbital, only 2 per orbital. So if we had an extra electron, say we had say we tried to do this, like that. Right? 1 hydrogen ion with 2 electrons and 1 electron here. So we'd have 3 electrons. We'd have to put 1 of them up here. So that would weaken the bond. We got 2 down here, but 1 up there that weakens this bond. And it might form, but it would be, of course, it would have a negative charge. Okay. Okay, how about fluorine? Let's take that out, take that out, take this out, take that out. How about fluorine? Right? Fluorine has 18 electrons. And this is the shorthand way of representing it. Let's do fluorine this way, and then we'll move to the shorthand way. Okay, so let's just take that out. Okay. We would draw atomic orbitals for the individual fluorines. Okay, but way down here we got 1s orbitals. About right here. Let's see, 1s. 1s. Okay, then we have 2s. About right here. And then we have 2p's. Right? 2p's have 3 orbitals. Right? X, Y, and Z. Is that all we have? Yeah, that's all we have. Okay, each fluorine has 9 electrons. So we have 2, 4, 5, 6, 7, 8, 9. Well, there we have our atomic structures. And we're going to construct molecular orbitals from them. Since they're both the same, it's a very symmetrical approach. When you start getting different atoms, like you try to put a fluorine together with I don't know, a sulfur, then the orbitals kind of drift like this, and you need a little more math than I've got to explain what you do with the molecular orbitals. So we're using a symmetrical approach at first. So these two right here are going to be two molecular orbitals. We're going to have one here, one here. So this is a sigma 1s and a sigma star 1s. Then we're going to have one here, one here. This is going to be a sigma 2s and a sigma star 2s. Then we're going to have a sigma right here, a sigma derived from a p. And then we're going to have a sigma star derived from the p's. All right, so that's two. We got six, and we got two of them so far. So the others are here and here. So now we have a pi and a pi from the 2p, and we have a pi star and a pi star from the 2p's. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's all of our molecular orbitals. I should have stretched them out a little more, but too late. All right, now we have 2, 4, 6, 8, 10, 12, 14, 16, 18. We got 18 electrons total. So we start at the bottom. 2, 4, 6, 6, 8, 10. Remember the Hun rule: 10, 11, 12, 13, 14, 15, 16, 17, 18. There we go. So we've used them all up. And we didn't have to use this one. So when we translate that into shorthand, lowest energy from the left, this is like electronic structures, right? Left to right, low to high energy. So the sigma 1s, then the sigma star 1s, then the sigma 2s and the sigma star 2s, then the sigma 2p, then the pi 2p, right? We didn't split that 2p. It's got two orbitals in it. So 4 electrons go in that one. And then the pi star 2p. And we have 2, 2, 2, 2, 4, 4. That's the shorthand. Okay? Now, for convenience, sometimes we only write the valence electrons. So we would leave this whole group out here. Right? And just consider the valence molecular orbitals. Just realizing that these do exist. It's more convenient and less messy if you just focus on the valence. And the calculations that we're going to do with them will work out just fine using only the valence. We'll get to that on this slide. Bond order. Bond order is kind of second cousin to what we've described in the past as single, double, and triple bonds. Bond order is a way of measuring the strength of the bond, right? So if it's a bond order of 1, it's more like a single bond. It's a bond order of 2, it's more like a double bond, so forth. The one major difference between bond order and single, double, and triple bonds is that we can have fractional bond orders. We can have half a bond order. We can have 1, 1.5, 2, 2.5, 3, 3.5. We can, have bond orders of fractional design. Okay, so what do? For a bond order, we take the number of bonding electrons, right? In this case, it would be 2, 4, 6, 8, 10. 10 bonding electrons. and subtract the anti-bonding. So there's 2, 4, 6, 8, minus 8, anti-bonding. And divide by 2. Because there are 2 electrons in every bond. So that's 2 divided by 2 equals 1. That's the bond order for fluorine. And we know from measurements that between the 2 fluorine atoms is a single bond. Bond order 1. So as far as that goes, it matches up. Okay. So the bond order of hydrogen then would be, we had 2 bonding and no anti-bonding. Remember that? So 2 minus 0 divided by 2 is 1. So there's a single bond for the hydrogen atom, the dihydrogen atom. If we add an electron like I did before, where we had one of those came in with an extra electron, we have to add that one to the anti-bonding. So now it's 2 minus 1 equals 2, divided by 2 equals a half. So we've decreased the strength of that bond from a 1 to a half bond order. We've weakened the bond. Doesn't mean it can't exist. It just means that it's weaker. Oh, okay.
Today we're going to discuss molecular orbitals. But before we can get to molecular orbitals, we have to first consider atomic orbitals, something that hopefully we're all pretty familiar with. So let's start with hydrogen. Here I have 2 isolated hydrogen atoms. And we know that each isolated hydrogen atom should have 1 electron located in the 1s subshell when in its ground state. And of course we know that these electrons don't move in perfect circles around the nucleus as I've depicted them here, but they do define a region of space defined by a sphere. But when 2 atomic orbitals combine to help form a chemical bond, something special happens. In the case of hydrogens, those 2 1s subshells combine and form a region of space known as a sigma molecular orbital. And a sigma molecular orbital is a region of space where the electrons live generally in between the 2 hydrogen nuclei, screening the repulsive force that their positive charges have on one another. So they stabilize, keeping these 2 nuclei close together. This is a bonding molecular orbital. But there's one rule that we haven't yet considered, and that is that the number of atomic orbitals going into an MO system must be equal to the number of molecular orbitals that that MO system contains. So our molecular orbital system is not yet complete in this depiction. We have 1 more molecular orbital that forms. That new molecular orbital that forms is called a sigma star molecular orbital. And it looks quite different from the sigma MO, doesn't it? If there were electrons inside of this sigma star molecular orbital, they would spend most of their time outside of the 2 nuclei, not screening their positive charge repulsions, and therefore would actually make the system very, very unstable. So let's think about what that means in terms of how hydrogen atoms come together to form a bond. In order to fully understand the molecular orbitals of an H2 molecule, we have to plot them in terms of energy. So here in this depiction, I've shown the 2 atomic orbitals here as these lines in blue. That will be our non-bonding energy. Unless there's an energetic benefit to forming molecular orbitals, these 2 atoms aren't going to get together and do that. So bonding molecular orbitals will be lower in energy, and antibonding orbitals will be higher in energy than this purple line that I've drawn. So let's combine these 2 different atomic orbitals into molecular orbitals and see what happens. When this happens, we always get a combination that is sort of centric around that non-bonding energy. In this case, we formed 2 new molecular orbitals from our 2 atomic orbitals. One is the sigma, one is the sigma star. Next, we have to populate our new molecular orbital system with the electrons that we know the atoms are bringing to the party. In this case, 1 from each. When we do this, notice that those electrons go into a lower energy orbital overall, and this lowers the overall energy of the entire system. So this energetic benefit that comes from forming and populating molecular orbitals leads us to the prediction that hydrogen will form a bond to another hydrogen. But beyond that, we can actually calculate exactly how many bonds will form. We call this the bond order, and it's calculated quite simply, using the number of bonding electrons minus the number of antibonding electrons, divided, of course, by 2, because we know it takes 2 electrons to form a chemical bond. In our example here of hydrogen, we have 2 bonding electrons, and we have no antibonding electrons. Consequently, our equation tells us that we expect 2 hydrogen atoms to get together and form a chemical bond with an order of 1. In other words, a hydrogen molecule should have a single bond. And that is, in fact, exactly what we see. Now let's move on to the next element on the periodic table, helium. Now I've put molecular orbitals here in quotations because, as we're about to discover, there really is no such thing as a helium-2 molecule. But to prove it, we need to use our energy diagram and combine the 2 atomic orbitals of helium atoms to find out what the energetics of bonding would be if it were to happen. So let's go ahead and do that now. We combine them into a system with a sigma and sigma star molecular orbital, and then we populate that system. Now, in this case, I have 2 electrons that can fill the sigma bonding molecular orbital, lowering the overall energy. But I still have 2 more electrons that have to go into this new molecular orbital system. And they have no choice but to go up in energy and populate the sigma star. The consequence of this is that there's no real energetic benefit to bonding. So 2 helium atoms have no real incentive to get together and form an He2 molecule. And in fact, that's exactly what we see. When we calculate the bond order, we find that 2 bonding electrons and 2 antibonding electrons leads to a situation where we predict a bond order of 0. In other words, we don't predict a bond at all. And when we study helium in the laboratory, that's exactly what we find. Helium exists as isolated atoms. Now let's expand our discussion and consider the molecular orbitals of elements from the second row of the periodic table. We're going to begin with fluorine. Now, fluorine, we know, has available p orbitals because it's in the second row of the periodic table. So atoms of fluorine have 3 different 2p orbitals to donate to forming new chemical bonds. And within those orbitals, we know each has 5 electrons. So let's think about, first, how those atomic orbitals combine, and second, how those electrons can populate the new system energetically to make something that's beneficial. When we combine p orbitals, we find that we have a system that looks a bit different, don't we? In this case, a grand total of 6 atomic orbitals must combine to form a grand total of 6 molecular orbitals. Now, the lowest and highest in energy of these correspond to the in-phase and out-of-phase overlap directly along the nuclear axis. Those we would call the sigma and sigma star molecular orbitals. But we have some new players here. Those are the orbitals that result from the side-to-side overlap of p orbitals that we call pi and pi star MOs. So we have to figure out exactly where the electrons will go in this system and whether or not there's a real energetic benefit to putting them there, and that will help us determine whether or not fluorine will make a bond. Let's do that now. When we put all of our bonding electrons in, we notice that 6 total electrons go into bonding molecular orbitals. This is a tremendous energetic benefit. The sigma and the pi bonding MOs are completely filled. But fluorine has extra electrons, and they have to go somewhere. And the next best available option is to place them into the pi star molecular orbitals. These are antibonding, so the energy comes back up somewhat. However, notice that overall, we still have a system in which, on average, our electrons are in lower energy locations when they're in the molecular orbital system. There's a little bit of an energetic benefit here. And our calculation for bond order lets us know that when you have a grand total of 6 bonding electrons and a total of 4 antibonding electrons, you would expect that species to form a single bond. And in fact, when we study fluorine in the laboratory, that's exactly what we find. A molecule with a single bond. Now let's move on to something a little bit more complicated. Here's another second row element, nitrogen. Nitrogen also has 2 p atomic orbitals available, but in this case only 3 electrons in each. So let's combine those and form a new molecular orbital system. You might notice something changed here, right? Notice that the sigma molecular orbital is actually higher in energy than the pi. And this is an interesting phenomenon. It's caused by something called sigma pi mixing. And we won't go into great detail into it here, but I wanted to point it out because this is how you'll probably see it in your textbooks. Nonetheless, when we use the electrons from nitrogen's 2p orbitals to populate this new MO system, notice that they all go into bonding MOs. And better than that, there's nothing left. There are no extra electrons to fill in those antibonding MOs and counterbalance the energetic benefits. So this is a tremendously energetically beneficial arrangement. When we calculate the bond order of an N2 molecule, we find that having 6 bonding electrons and absolutely no antibonding electrons, we expect a nitrogen molecule to have a triple bond. This is a very strong bond, which makes nitrogen gas almost completely inert. And again, when we go into the lab and study nitrogen, that's exactly what we see. A diatomic molecule with a triple bond. Now let's consider one more element from the second row of the periodic table. This time we'll consider oxygen. And I promise, I'm not wasting your time here. We're going to see something new. Now, just like any other second row element, oxygens have available 2p subshells. And we know from their electron configurations that each oxygen contains 4 electrons in those 2p subshells. So let's combine them to form some molecular orbitals. When we do this, we don't see any real surprises here. Sigma, sigma star, pi, and pi star molecular orbitals form. 6 atomic orbitals in, 6 molecular orbitals out. And if we fill them from the lowest energy to the highest, we notice that 6 of these electrons will go into bonding molecular orbitals, giving us a nice energetic benefit. But there are still 2 remaining electrons. And here's our new question. They clearly should go to the pi star MO, but should both electrons go into one, or should they each take a separate molecular orbital for themselves? The answer to the question is rooted in Hund's rule and the Pauli exclusion principle. Electrons will try to spread out and maximize spin. So, when they populate this new molecular orbital, they do so like this, raising the overall energy a little bit, right? Not enough to completely counteract all of those bonding electrons, so there will be a bond formed here. O2 molecules do exist. But even more importantly than that possibly is this. Notice that there are unpaired electrons in this molecule. And that means that our new oxygen molecule is paramagnetic. Liquid oxygen can be trapped within the confines of a powerful magnet. You may have seen this demonstration done before. And of course, just as before, our prediction is correct. If we calculate the total bond order of oxygen using 6 bonding electrons and 2 antibonding electrons, we find that the 6 and the 2 leads us to a calculated bond order of 2. Oxygen exists as a diatomic molecule with a double bond. So I hope that by now you're beginning to appreciate the power of molecular orbital theory. It not only confirms so many of the other topics we've already discussed on bonding, but it allows us to explain completely new properties that all of our other theories couldn't, things like the paramagnetism of oxygen. This is just the beginning of molecular orbital theory. You may want to consider in the future things like molecules that consist of 2 atoms that are not the same, or molecules that consist of even more than 2 atoms. There's much, much more to explore. But for this lecture, we're done. Thanks for watching, everyone.
Okay. There was a mention in there of non-bonding. You can have in some circumstances, and I'm not sure how they come up with this. It's math is too much for me. Is you can come up with non-bonding orbitals formed from these combinations. And when you do, they are at the same energy level as the atomic orbitals that form them. You don't get that split. I mean, they're just right there. Okay. We're not going to dig into that too much. There was also a mention of paramagnetism and diamagnetism. Paramagnetism is a phenomenon of molecules drawn into a strong magnetic field. Diamagnetism is the opposite. Molecules repelled by a strong magnetic field. Now, the importance of this is in the way that the valence bond theory approaches with its Lewis dot structure, and the way that this approaches the valence bond theory does not predict the correct paramagnetism or diamagnetism of these molecules. Oxygen's a good example. Right? If we have dioxygen here, right, then our Lewis dot structure would do this, right? C times 12, 2, 4, 6, 8, 10, 12. That's what our Lewis diagram would show us. And it says all these electrons are paired. Well, when you have paired electrons, they have opposite spins. So they cancel each other out. And when they cancel each other out, they should yield a diamagnetic molecule, one that's repelled by the magnetic field. But we know that oxygen is attracted to a magnetic field. And let's see, here it is. There it is. There's liquid oxygen being poured into one of those big horseshoe magnets, and it stays right there. The molecular orbital model for oxygen gives us two unpaired electrons. You saw it in the film, in the video. At two unpaired electrons, that means that it should be paramagnetic. So the molecular orbital model correctly predicts paramagnetism for oxygen, whereas the valence bond theory does not. Okay, let's go back. There. Okay. So up to this point, we are describing homonuclear diatomic molecules because they are the easiest to understand. You have two identical atoms with the same elements being bound together. And we typically only are interested in the valence electrons. In fact, the presenter of this video wasn't even using all the valence electrons. He stayed with the p orbitals, and the description was perfectly good for calculating bond orders. All right. Diamagnetism is characteristic of nitrogen. If you pour liquid nitrogen through that magnet, it'll go straight on through without stopping. And we can measure diamagnetism and paramagnetism in terms of the force that's applied. So as we lower our sample into that strong magnetic field, it's either attracted to it, which will cause the balance to give me an added mass, or it's repelled, which will decrease the mass. Oh, Professor Dave wants to talk. Let's see. It's a little after 2. And we're good till 3:50. Okay, we'll let Dave talk.
It's Professor Dave. Let's revisit molecular orbital theory.
He knows a lot about the science stuff. Professor Dave explains.
We've learned a bit about molecular orbital theory and the ways in which it differs from valence bond theory. But let's expand on this knowledge now so that we can understand a phenomenon called sp mixing. But before we get into that, let's take some time to review the basics. First, let's compare valence bond theory and molecular orbital theory. Valence bond theory considers covalent bonds as being localized between a pair of atoms, resulting from the overlap of atomic orbitals or hybrid atomic orbitals. This overlap results in sigma or pi bonds, and we can use this theory to predict molecular shape. However, there are simple molecules that do not conform to this theory, like the diatomic oxygen molecule. Given this Lewis structure, where each oxygen atom has a full octet, we would expect oxygen to be diamagnetic and weakly repel a magnetic field. However, it does in fact exhibit paramagnetism, as liquid oxygen is attracted to a magnetic field. To explain this, we have to turn to molecular orbital theory, which differs from valence bond theory in that electrons are considered delocalized throughout the molecule, and atomic orbitals combine to form molecular orbitals, which are also delocalized throughout the molecule. These can be sigma and pi bonding orbitals, or sigma star and pi star anti-bonding orbitals. This theory ends up being better equipped to predict the arrangement of electrons in a molecule in certain situations. This is due to a process called the linear combination of atomic orbitals. In the modern physics course, we talked a little bit about the wave function, and molecular orbitals are combinations of atomic orbital wave functions. Just the way the wave function describes the behavior of an electron within an atom, molecular orbitals describe the behavior of an electron within a molecule. And just like atomic orbitals, they are filled when they contain two electrons of opposite spin. This theory requires that we strongly consider the wave nature of the electron. In the classical physics series, we talked a lot about waves and interference patterns. So to get the full picture of wave behavior in order to better understand molecular orbitals, check out this tutorial now. Otherwise, we simply need to understand that when two atomic orbital wave functions are combined, like these two s orbitals, there can be constructive interference, where the peaks line up with the other peaks. This causes the amplitude to increase, which results in a bonding molecular orbital, like the sigma s orbital. Most of the electron density is between the nuclei, which strengthens the bond. There can also be destructive interference, where the peaks line up with troughs. This causes the amplitude to drop to zero, resulting in an anti-bonding orbital, like this sigma s star orbital. Here, there is a node between the nuclei, which weakens the bond. The bonding orbital is of lower energy and will thus be filled before the anti-bonding orbital. For this to make more sense, we simply need to understand that these images of waves are just two-dimensional analogies to help us visualize the type of overlap. Electrons are three-dimensional objects, so the waves are in 3 dimensions, and constructive interference thus results in regions of greater electron density, while destructive interference results in regions of no electron density, which are depicted by these bonding and anti-bonding orbitals. We can do the same thing with p orbitals, utilizing direct overlap, which will yield sigma px and sigma px star molecular orbitals, or lateral overlap, yielding pi and pi star molecular orbitals from the overlap of py and pz atomic orbitals. Orbital number is always conserved, which is why the linear combination of two atomic orbitals will always result in two molecular orbitals, one bonding and the other antibonding. We can depict these linear combinations with molecular orbital diagrams, as we have seen. The dashed lines show how the atomic orbitals on the sides combine to form the molecular orbitals in the middle, such as we see here for hydrogen, with two 1s orbitals combining to form one sigma s orbital and one sigma s star orbital. If we go up to the electrons in the n=2 shell, we can see the 2s orbitals combining in precisely the same way, and then the 2p orbitals combining as follows, with the sigma bonding orbital and then pi bonding orbitals, followed by the corresponding anti-bonding orbitals. The good news is that these orbitals are still filled according to the Aufbau principle and Hund's rule, like we already know. This means that we fill them from lower energy to higher, according to Aufbau, and we will put one electron in each orbital for a set of degenerate orbitals before doubling them up, according to Hund. We've already learned in a previous tutorial how to fill in these MO diagrams for certain diatomic molecules, like O2, and how to use them to calculate bond order. Here's that diagram one more time, along with the calculation for bond order, with 10 bonding electrons, including the sigma 1s bonding electrons, and 6 anti-bonding electrons, including the sigma 1s star anti-bonding electrons. 10 minus 6 is 4, and 4 over 2 is 2. This explains the double bond in diatomic oxygen. But we also get an explanation for the paramagnetism of the oxygen molecule. We have two unpaired electrons in these antibonding orbitals, which does predict paramagnetism for this molecule. This is an example of the success of molecular orbital theory, as no other theory can account for this behavior. Now that we are up to speed, let's go over one other thing. The molecular orbitals that result from the combination of the 2p orbitals exhibit this order in O2, but this will change for other homonuclear diatomic molecules. Let's look at this diagram, which depicts the relevant orbital energies for all the potential homonuclear diatomic molecules in the second period, from lithium to neon. As we go to the right in the period, effective nuclear charge increases, so the atomic radii contract, and the orbitals get lower in energy. On the left, the pi 2p bonding orbitals are lower in energy than the sigma 2p bonding orbital, but on the right, the sigma 2p bonding orbital dips below and thus will be filled first. This discrepancy is due to a phenomenon called sp mixing, which influences the energies of these molecular orbitals. This happens when the sigma s and sigma p wave functions combine in such a way that the sigma s orbital becomes more stable and the sigma p orbital becomes less stable. As a result, we see the sigma s and sigma s star orbitals going lower in energy and the sigma p and sigma p star going up in energy. So much so that the sigma p orbital now sits above the pi p orbitals. Molecules like O2 and F2 have negligible sp mixing because the 2p orbitals in those atoms have some paired electrons. This raises the energy of the 2p orbitals, making them too dissimilar to the energy of the 2s orbital to allow mixing to occur. But going to the left on the period, where p orbitals have unpaired electrons or are vacant, the 2p and 2s orbitals are of similar enough energies that sp mixing will be prevalent and the order of the molecular orbitals will switch. While this is an interesting phenomenon, if we are only using these diagrams to calculate bond order, it won't matter because it is just the order of bonding orbitals that is being rearranged, so it won't affect a bond order calculation. Nevertheless, we have hopefully reached a more sophisticated understanding of molecular orbitals. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.
No, it isn't. So here's that diagram he was showing us. The easiest way to know, notice that with no mixing, you have this arrangement. You have the sigma 2p here, and the pi 2p here. When you get mixing, then the pi 2p, it inverts with the sigma 2p. So you would have then, instead, you would have the pi 2p's down here and the sigma 2p here. So they would flip. When does that occur? Well, the easiest way for us, since we're not going to dig too deep into the periodic table, is to draw the line between nitrogen and oxygen and phosphorus and sulfur. So to the right, the oxygen and fluorine have no mixing. That means that the sigma comes before the pi in energy. And then to the left, nitrogen and over, it flips to this situation where the pi comes first and the sigma comes second. That's the easiest way to deal with it, right? If you just memorize the one on the right, and then when you get left of oxygen, just flip those two, you'll be good to go. Now, very often what you see in proper descriptions of these in textbooks, rather than SP mixing, they're going to say sigma pi mixing. And here's an expanded chart that shows the nitrogen, dinitrogen, dicarbon, diboron on the left with mixing, and the oxygen and fluorine on the right with no mixing, and the consequent magnetism, depending on whether you have paired or unpaired electrons. So the diboron does have unpaired electrons. It's paramagnetic like oxygen. The others are diamagnetic. And the calculated bond order, actual measurements of bond energy and bond length. Remember, as the bond energy increases, the length decreases. So dinitrogen is going to have a very, very short bond by comparison to diboron. Okay. Now here's where it becomes a little more actually than I think this course is equipped to expect of its students. But I do need to introduce the topic of heteronuclear diatomic molecules. In this case, we've got carbon and oxygen, carbon monoxide. So notice that carbon being to the left of oxygen and having a lower effective nuclear charge, then the energy of the orbitals is going to be up because you don't have those extra protons drawing those electrons down, shrinking the orbitals. So the carbon is going to be high. It's going to start off higher with its atomic orbitals. Oxygen is going to start off lower. And then you need an understanding of how these orbitals are combined in order to get them in the correct order. For carbon and oxygen and carbon monoxide, it looks like we have a sigma S, a sigma P, pi, sigma star. In that case, the sigma star is it's above the pi's. Okay, so we did get some mixing there because we inverted. Anyway, you still, if you're given the structure, then you should be able to fill it with electrons. Right? You just count the number of electrons for carbon, for oxygen, and then fill them in the middle from bottom to top using the Aufbau principle and Hund's rule. Here's another example where hydrogen only has one S. And fluorine, which one mixes with the 1s orbital for hydrogen? Well, the one that's closest to it in energy. So the fluorine, the closer in energy to the 1s in hydrogen is the 2p. That's the one that we're going to mix and get a sigma and a sigma star. Okay. We still have to recognize, let's go back to the energy diagram. Notice that these two electrons in the molecular orbitals are closer in energy to the fluorine atom, which is another way of saying that those electrons, the electron density in the bond is shifted slightly toward the fluorine. And we know from past experience that this is a polar bond because fluorine is more electronegative than hydrogen. And this is another way of expressing it because the molecular orbital is closer to the fluorine atomic orbital that went into the mix. And then this diagram is trying to show you the shift in density toward the fluorine. Okay, that's what I just said. Delocalization. When we say delocalization of electrons in a bonding system, we mean that the electrons are effectively spread out over a larger volume. And that's one of the ways, one of the fingerprints of that type of scenario is resonance. When we see resonance, we think delocalization, because delocalization of any bonding system will stabilize it. Just think about it this way. If you try to concentrate electrons into a smaller region, the strength of repulsion is going to be greater. So if you can spread them out, then you minimize the repulsive effect. Here's a perfect example of delocalization, and that is resonance in the benzene molecule. Benzene molecule is extremely stable. It's difficult to break a benzene into pieces. And I was first introduced to that in soil chemistry when we were looking at how organic molecules, biomolecules, are broken down gradually. Say a tree falls in the woods, what happens first? Well, you get beetles and things come in there and break it into smaller chunks. And you get fungi coming in there with their cellulolytic enzymes able to break down cellulose. But it takes longer to break down other polymers in that wood. The ones that are composed of polymers of these benzene rings, they are the most resistant to decomposition because the bonds are a lot stronger. It's a more stable molecule. So our resonance structure here only has two structures, right? And wherever those lines meet, you got a carbon. Right? Just remember that about organic chemistry shorthand. Here's how that happens. If you hybridize the carbons to sp2s so that you can get a hydrogen on each carbon and a carbon on either side of the carbon, that gives you a 120-degree bond angle. Then what do you have left over? If you've got an sp2 hybrid, you've got one p left over. So those p orbitals are right. So you could do it like this. Those p orbitals are like this, right? They're all perpendicular to the plane of the molecule. And you get overlap here. You also get overlap there and there, there, and there, and there. So all of those p orbitals overlap in a continuous donut around the top and the bottom of the molecule. And that delocalization, this we call it a pi system. This delocalization stabilizes the molecule. This happens also in conjugated double bond systems. Conjugated double bonds are those in which we have a chain of carbon, right? Each one of these is a carbon, right? And if you have a double bond alternating with singles, then you get a similar pi system developing over the entire molecule, as long as it's a continuous double, single, double, single, double, single. And that stabilizes the molecule also. You see that in, let's see. Well, from my experience, you see it in carotenoids, like the pigments that make lobsters red. I wasn't working with lobsters at the time. I was working with crawfish. But one of the carotenoids, astaxanthin, has this conjugated system, and that's what makes them look red. Because if you lower the energy of these electrons in that system, then they move down into the visible range. Lower energy means more stable. We can do the same thing with this resonance structures for nitrate ion, NO2 minus. And this is what it would look like if I think I showed you this before, where you try to show the bonds are equal by putting, instead of double bonds anywhere, you put half bonds, right, dotted lines in there. But actually, this is what it should look like. This pi system is distributed over the entire molecule, which it makes it very stable. Now, this last slide is an attempt to offer evidence for the molecular orbital model. This is called photoelectron spectroscopy. So we take a molecule and we construct a molecular orbital model for it. And with that model, we can assign energies to each of these orbitals, right on up to the highest level that's occupied by electrons. And even beyond, if you promote them by adding energy, you can promote them into higher levels. But we can, with the molecular orbital equations, we can predict accurately the energy at each one of those molecular orbital levels. And this technique confirms those energies. So if we shine high energy light on this molecule and the energy in it is absorbed by this high level, or successively, actually we can shine on so much of it that we kick off these electrons and these electrons all the way down. And we can get a spectrum, like a list of energies for each of those electrons. The way we do that is we take the light energy that went in and we measure the kinetic energy of the electrons as they come out, right? Because the energy that we put in is enough to promote them to infinity. And that energy plus whatever's left over gives them kinetic energy, right? So if we measure the kinetic energy of those electrons as they exit the molecule and subtract that from the energy that we put in, we assume that the light energy difference between what went in and the kinetic energy that came out is the energy required to promote it from this level to infinity. And that's what this spectrum represents. And it accurately predicts the calculated energy for each of these molecular orbitals. Okay, does that make sense? Sort of. And that's it for this chapter.